Welcome back to Introduction to Software Reverse Engineering. In this module, we will continue exploring our example program and learn about various calling conventions in use on a 32-bit Windows platform. We will also learn about floating point number representation and the IEEE 754 standard. And, as a bonus, we will review 64-bit number addition on a 32-bit platform. Let's dive in. In this module, we are going to explore how C and C++ programs compiled with Visual C++ 6 for 32-bit Windows handle function calls. We will also explore the IEEE 754 floating point number standard. You might wonder what floating point numbers have to do with reverse engineering. The truth is, many programs rely heavily on floating point operations, and knowing how these numbers are represented in memory and in binary files can be a huge time saver. Let's start. In this module, we will continue reverse engineering our introductory example program, which is available on the GitHub alongside its source code and other examples. At its core, a calling convention is a set of rules that dictate how functions or subroutines receive parameters from their caller and return results. But why do we need these calling conventions? Well, without them, we'd be facing a world of problems. Imagine a scenario where every function call was a wild west of parameter passing and stack management. We would see crashes and instability, security vulnerabilities would be rampant, and compatibility issues would be the norm. Calling conventions bring order to this chaos. They ensure correct function calls, maintain stack integrity, enable interoperability between different code modules, and even allow for performance optimization. So what exactly do calling conventions specify? They define the interface of called code, including the order in which parameters are allocated, how they are passed, which registers are preserved for the caller, and how the stack is prepared and restored before and after a function call. By following these conventions, we can write more efficient, reliable, and secure code, and as reverse engineers, we can better understand how existing code works. Let's take a look at some common calling conventions used in C and C++ programs on 32-bit Windows. We'll be covering four main conventions: C declaration, standard call, fast call, and this call. First, the C declaration. This is the default calling convention in C, and it's characterized by the caller cleaning up the stack. Parameters are passed from right to left, which makes it well suited for variable argument functions like printf and scanf. Next is the standard call. In this convention, the callee is responsible for cleaning up the stack. Parameters are still passed from right to left, and this convention is commonly used for Windows API functions. The fast call calling convention is designed for performance. The first two parameters are passed in the ECX and EDX registers, while the remaining parameters are passed on the stack from right to left. The callee is responsible for cleaning up the stack. Finally, there is this call calling convention, which is used for C++ member functions. In this convention, the this pointer is passed in the ECX register, and parameters are passed on the stack from right to left. Again, the callee is responsible for cleaning up the stack. The C declaration is the default calling convention in C. One key characteristic of the C declaration is that the caller is responsible for cleaning up the stack. This means that after a function call returns, the caller must restore the stack pointer to its original state, effectively cleaning up the stack. Another important aspect of C declaration is that parameters are passed on the stack from right to left. This means that when a function is called, the last parameter is pushed onto the stack first, followed by the second to last parameter, and so on. The C declaration is particularly useful for variable argument functions, such as printf and scanf. These functions can take a variable number of arguments, and the convention provides a flexible way to pass these arguments on the stack. In this module, we will review and reverse engineer these three highlighted functions, as shown on the screen. They are quite simple, however, they are following different calling conventions. Let's go back to Ghidra and look again at the main function that we examined in the previous module. Take a look at the function on line 12. Now, take a look at the assembly instructions before and right after the function call. As you can see, one value was pushed onto the stack right before the function call, and the stack position was adjusted after the function return. This is a clear sign of a C declaration function call. Let's review the C declaration once more. The function parameters are being passed via stack in the right to left order. The stack is adjusted by the caller after the function call returns. Let's take a look at the cDeclaration function that is shown on the screen. Note that Ghidra correctly recognized the function calling convention. The cDeclaration attribute is shown in the decompile window as well as in the listing window. Click on the data member in the function on line 5 to see its content in the listing window. Ghidra will update the listing window and scroll to the data member location within the binary. Observe that the value was identified as undefined2, which is a 16-bit value. Let's change the data type to short. To do so, right-click on the value to bring up the context menu. Once the context menu has appeared on the screen, select Data, choose Data Type menu option to change the data type. The Data Type Chooser dialog will appear on the screen showing undefined2 as the current data type. An undefined2 data type is one of the built-in data types in Ghidra that signifies that the value occupies 2 bytes. Ghidra has multiple undefined data types for data of various length, from 1 to 8 bytes. Change the data type from undefined2 to short, and click OK to apply the change. Once the changes are applied, Ghidra will update both the listing window and the decompile window. The data member name has changed in both windows to reflect the newly applied data type. Now, let's rename the function. To do so, right-click on the function name in the decompile window and select Rename Function context menu item. The Rename Function window will appear on the screen with the current name of the function displayed. Type add short as the new name and click OK to apply the change. The new name will be applied and displayed in both the decompile window and the listing window. Note that Ghidra allows for multiple functions to have exactly the same name, which might create confusion through the reverse engineering analysis. Navigate back to the main function by double-clicking on the main function name in the cross-reference user interface element in the listing window. After all these changes, the main function will also show the new function name, addShort. Let's take a look at the Microsoft Fast Call convention. This calling convention is designed to improve performance by passing parameters in registers instead of on the stack. In Fast Call, the first 2 parameters are passed in the ECX and EDX registers. This allows for faster access to the parameters, as registers are generally quicker to access than memory. Any remaining parameters are passed on the stack, and they are pushed from right to left, just like in the other conventions. However, unlike the cDeclaration, the callee is responsible for cleaning up the stack in Fast Call. By passing parameters in registers and having the callee clean up the stack, Fast Call aims to reduce the overhead of function calls and improve overall performance. Now, let's take a look at the Fast Call function. Observe that instead of pushing value on a stack, compiler generated code that assigns a value of b to register ECX before calling the function. When using Fast Call, the first 2 parameters are passed in the ECX and EDX registers. This allows for quick and efficient access to these parameters. Any additional parameters are then passed on the stack, pushed from right to left, using push instruction. Once the function call is complete, the callee is responsible for cleaning up the stack. Let's look at the function itself. Again, Ghidra properly identified the calling convention and applied Fast Call attribute to the function. Take a look at the function's body, lines 8 through 12. It has a lot of moving parts. To go further, let's inspect the source code of this function. The source code of the function is straightforward. It adds the function argument to a previously allocated variable. However, the type of the variable is int64, or long in modern versions of C. This data type is a 64-bit integer data type. Now, let's take a look at the compiled code once more to figure out why a simple addition was transformed into so many instructions. The reason for this is that the program is compiled to be executed on a 32-bit CPU, while the variable is a 64-bit value, which does not fit into a CPU register for direct computation. Let's talk about performing 64-bit addition on a 32-bit platform. You might wonder how this works given the limitations of a 32-bit CPU. The key is to break down the 64-bit numbers into smaller, manageable chunks. To do this, we split each 64-bit number into 2 32-bit parts, the low 32 bits, which contain the least significant bits, and the high 32 bits, which contain the most significant bits. We then perform the addition in two stages. First, we add the low 32 bits of both numbers. This produces a 32-bit result and potentially a carry flag if the result exceeds 32 bits. Next, we add the high 32 bits of both numbers, including the carry flag from the previous step. This ensures that the carry is propagated correctly, giving us the final 64-bit result. By breaking down the operation into these two stages, we can accurately perform 64-bit addition on a 32-bit CPU. Equipped with this knowledge, let's take a look at the function once more. This time, let's look at the data members. Click on the data member displayed on line 10. Ghidra will show you the data member as well as the second data member used in the function and their values as independent 32-bit values. Let's change the data type to a 64-bit long data type. To do so, right-click on the value and the Select Data, choose Data Type Context menu option. The Data Type Chooser window will appear on the screen. Type in long as the new data type and click OK to apply changes. Once the data type is applied, the windows will update. With the 64-bit integer value operations now displayed as operations on its lower 4 bytes as well as the operations on its higher 4 bytes, it does look like the addition with a carry. Now, let's rename the function so that it has a better name. To do so, right-click on the function name to bring up the context menu and click on Rename Function option. The Rename Function window will appear. Type in add short to long as the new name and click OK to apply the changes. The new name will show up in the listing window as well as the compile window. Now, double-click on the main function name in the cross-reference user interface element to navigate back to the main function. The main function will show the new name of the function in addition to the new name of previously analyzed function. Let's take a look at the standard call convention. This convention is widely used in Win32 API function and is characterized by a few key features. First, the callee is responsible for cleaning up the stack. This means that the function being called will handle the task of restoring the stack pointer to its original state after the function call is complete. Another important aspect of the standard call is that parameters are passed on the stack in the right to left order. By having the callee clean up the stack and passing parameters in the specific order, the standard call provides a standardized way for Win32 API functions to handle function calls, making it easier to write and interact with these APIs. The standard function call, shown on line 14, has the parameter passed on the stack, but it does not contain stack cleanup instruction in the body of the caller. The source code of this function is shown on the screen. It subtracts the value of the parameter from the same 64-bit variable examined earlier in the fast call addition function. Note that the standard call calling convention is only displayed as an attribute in the listing window, but not in the decompile window. Let's verify that it is indeed the standard call calling convention function. Right-click on the function name and select Edit Function Signature context menu option. The Edit Function window will appear on the screen with standard call displayed as the calling convention. When it comes to returning values from functions, the convention is to use specific registers depending on the type of value being returned. For integers and pointers, the return value is typically stored in the EAX register. This makes it easy for the caller to access the return value. For floating point values, the return value is stored in the ST0 register, which is part of the floating point unit, or FPU. When it comes to 64-bit integers or small structures, things get a bit more complex. In this case, the return value is stored in a pair of registers, EDX and EAX. The high 32 bits of the value are stored in EDX, while the low 32 bits are stored in EAX. This allows the caller to reconstruct the full 64-bit value or access the structure's content. The IEEE 754 floating point standard is a widely adopted standard for representing and manipulating floating point numbers. Developed in 1985 by the Institute of Electrical and Electronics Engineers, this standard provides a framework for consistent and predictable floating point behavior. One of the key features of IEEE 754 is that it defines formats for floating point values of various sizes, including 32-bit, 64-bit, 80-bit, 128-bit, and 256-bit values. This allows for flexibility in representing numbers with different levels of precision. The standard also specifies rules for arithmetic operations, rounding, and exception handling. This ensures that floating point operations are performed consistently and accurately, reducing the risk of errors and inconsistencies. By providing a standardized framework for floating point arithmetic, IEEE 754 has become a cornerstone of modern computing, enabling reliable and efficient numerical computations across a wide range of applications. Let's break down the format of a floating point number. A floating point number consists of three main components: the sign, exponent, and mantissa. The sign bit indicates the sign of the number, with a 0 representing a positive number and 1 representing a negative number. The exponent represents the power of 2, but is biased by a fixed value. For single precision, this bias is 127, and for double precision, it's 1023. This bias allows for a range of exponents, both positive and negative. The mantissa represents the fractional part of the number, and it's normalized to have a leading one, which is implicit. This means that the actual value represented by the mantissa is 1 plus the fractional part. The IEEE 754 standard defines several special values for floating point numbers. Let's take a look at these special values for 32-bit floating numbers. We have four special values: infinity, nan, subnormal, and 0. Infinity represents overflow or division by 0. Nan, or not a number, represents invalid or unreliable results. Subnormal numbers represent a very small numbers close to 0. These numbers are too small to be represented in the normal format, so they use a special format with an exponent of 0 and a non-zero mantissa. Finally, 0 represents an exact 0 value. Interestingly, IEEE 754 distinguishes between +0 and -0, which have different sign bits, but both represent the same numerical value of 0. These special values help handle edge cases and provide a more robust and reliable way of working with floating point numbers. The IEEE 754 standard defines several rounding modes for floating point numbers. There are 5 rounding modes: round to nearest, ties to even; round to nearest, ties away from 0; round toward 0; round toward positive infinity; and round toward negative infinity. The default mode is round to nearest, ties to even, which rounds to the nearest value. If the number falls midway between two values, it's rounded to the nearest value with an even least significant bit. This helps reduce bias in calculations. I encourage you to read special literature and articles on the internet to familiarize yourselves with details of the other floating point rounding modes. Let's take a look at how IEEE 754 floating point numbers are represented in Ghidra. In Ghidra, the floating point numbers can be represented as normal human-readable numbers as well as in their hexadecimal format. The hexadecimal representation allows the numbers to be represented and visualized when Ghidra is not sure about the true type of the value. The main function has a few examples of floating point numbers being used as the arguments to function calls. See lines 15, 16, and 17. On line 15, for example, Ghidra did not recognize the values as being floating point numbers, and they are displayed in their hexadecimal format. I encourage you to use hex to floating point calculators available online to convert these values to their normal floating point representation. Looking ahead to the next module, we are going to dive into arrays in Ghidra. We will review how arrays are stored in the data sections of a binary and how indexing works. We will also learn how to instruct Ghidra that values are indeed an array using its user interface. And we will use some basic logic in order to calculate the sizes of the arrays in question. And, as always, the course materials will be available on GitHub. If you are looking to dive deeper into software reverse engineering, I'd like to recommend my book, Software Reverse Engineering: Navigating x86 Windows Applications with Ghidra. This course draws heavily from the book's content. However, the book itself contains many more examples and insights that can help developing your reverse engineering skills. The book is available in both print and digital Kindle versions on Amazon, making it easy to access and read wherever you are. Additionally, the book covers subjects not discussed in this course, such as reverse engineering of C++ programs, classes, virtual functions, and more. I encourage you to check it out. Thank you so much for watching and learning with me today. If you found this video helpful, please hit that like button and subscribe for more content like this. Your support means a lot to me. If you have any questions or topic you'd like to discuss, leave a comment below or shoot me an email. I'm happy to chat. If you'd like to support me and the channel financially, you can do so through Ko-fi or Patreon. Links are in the description below. Thanks again for watching, and I will see you in the next video.